We've already introduced the benefits and opportunities for MetaCORE as a lightweight impact protecting material. We quantify impact protection with two numbers, SEA and CFE, that are measured in each of the X, Y, and Z directions. SEA, which stands for specific energy absorption, quantifies how much energy is absorbed in a unit mass of impact protecting material. Increasing the mass increases the amount of energy absorbed. Higher SEAs are better than lower SEAs, and the SEA can be different in different directions. For example, honeycomb has a high SEA in only one direction, whereas MetaCORE has been designed to have a high SEA in all directions. CFE, which stands for crush force efficiency, is a ratio of stresses that measure how much force travels through an impact protecting material. This number is used in aerospace and automotive industries as a way of determining the risk of head and neck injuries during a collision. CFE is inversely related to the size of the peak on this stress-strain graph. Larger peaks reduce the CFE to 0, offering the least amount of protection. Smaller peaks increase the CFE to its maximum value of 1, offering the most amount of protection. Honeycomb has a large peak stress, whereas MetaCORE was designed to eliminate this problem and has virtually no peak stress. These data highlight honeycomb's most critical limiting factor. It has one functional direction which narrows the operational envelope. MetaCORE was designed to function in all directions, giving a 30 times larger operational envelope. With these metrics in mind, let's do some demos. Our insurance policy won't cover us for ammo boxes or solid fuel rockets, so we're going to get creative. Our technical requirements are 1. A high-density payload, 2. A sensitivity to impact, 3. A clear measure of survivability, and 4. It's easily bundled in a containerized delivery system. In other words, water balloons. Our loading dock is no Yuma proving grounds, but this approach allows us to do low-altitude drops of high-density payloads to determine baseline survivability rates. We prep bags with 10 water balloons each and drop them from various heights in triplicate to measure survival. The bags are thin plastic and provide no meaningful impact protection. A height of 1.5 meters, or 60 inches, gives about a 40% survival rate, which is a good baseline for testing honeycomb and MetaCORE. We took inspiration from the enhanced speed bag delivery system, which is essentially a padded rucksack lowered from helicopters to provide express delivery of cargo and supplies. For our demonstration, we padded 2 rucksacks, one with off-the-shelf cardboard honeycomb, the other with off-the-shelf MetaCORE. This setup allows us to replicate airdrops under ideal circumstances where impact is in the normal direction and within the limits of honeycomb's operational envelope. We found both honeycomb and MetaCORE doubled the water balloon survivability, proving that MetaCORE can replace honeycomb as it's used today 1-for-1. The first demonstration mimics how airdrops are done today when loads are applied in the normal direction. But what about the other directions, which are outside honeycomb's operational envelope? We have reams of measurements acquired with our 250 kilonewton Instron universal tester quantifying the SEA, CFE, and omnidirectional impact protection capabilities of MetaCORE for comparison to honeycomb. Finite element simulations supporting our technical demonstration are available in a white paper we produced during our xTech experience. The data generated over the last 6 months proves MetaCORE delivers superior protection over honeycomb, enabling new types of payloads to be eligible for aerial delivery. Future airdrops with MetaCORE will increase soldier lethality because these payloads will be dropped faster, under tougher conditions, and with greater success rates.